Welcome back. So, in the last lecture we concluded by solving a question by using Buckingham pi theorem to obtain the time period here. Okay. And now we proceed back to our discussion of how to be able to choose the variables in Buckingham pi theorem. So, choosing variables, the first step is clearly define the problem, and we have to understand what is the main variable of interest or the dependent variable. In just the example that we have solved, that the time period was the dependent variable, and in the pipe flow problem that we have done before, there the pressure drop per unit length was the main variable of interest. Now, consider the basic laws that governs the phenomenon. Even a crude theory that describes essential aspect of the system may be helpful in cases like these. Now, you have to start the variable selection process by grouping the variables into three broad classes, which this we have already seen. One class is geometry, the other is material properties, and the third is external effects. That is, please consider other variables that may not fall into one of the above categories. For example, time will be an important variable if any variables are time dependent, right. You have to make sure to include all the quantities that enter the problem, even though some of them may be held constant. For example, acceleration due to gravity, right, but this should go into the problem. For a dimensional analysis, it is the dimensions of the quantities that are important, not specific values. Okay. So, don't miss any of those, even though they are constants. Sometimes we have the tendency of missing the constant values, for example, as it is mentioned here, the acceleration due to gravity, but that has to be taken into account because it is the dimension of the quantities that are important and not their values. You have to make sure that all those variables are independent. Look for relationship among subsets of those variables. So, another topic, that is uniqueness of pi term. The pi term should be very unique. So, before actually going to this, I would like to go and solve one problem here that I have included towards the end. So, the question is, there is a small sphere of density rho s and diameter d that settles at a terminal velocity v in a liquid of density rho f and the dynamic viscosity mu. Gravity g is known to be a parameter. Express the functional relationship between these variables in dimensionless form. So, what are we going to do? We will use Buckingham pi theorem. I just want to solve this problem so that you are able to practice a little more. All right. So, what we are going to do is going to white screen. So, like the problem last time, everything is given. So, it is given the terminal velocity v is a function of what are function? Rho s d rho f, okay, mu and g. See if we have missed any variable. So, it says small sphere of density rho s and diameter d settles at a terminal velocity v in a liquid of density rho f, dynamic viscosity mu and g. All right. So, first step is that we have to list the dimension of each variables. So, V is written as LT minus 1, rho S will be written as ML minus 3. I will do it very slow so that you are able to follow. Diameter has a dimension of L, rho F will have the same dimension as ML minus 3, mu will have the dimension of ML minus 1, T minus 1, and G will have LT minus 2. So, we have listed the dimensions of each variables as follows. So, K is 1, 2, 3, 4, 5, 6. So, K is 6 and R is basic dimensions. If you see, M is also appearing, L is also appearing, T. So, R is 3, which implies hence there are 6 minus 3 is equal to 3 dimensionless terms. Okay. So, these following some of the initial steps, we have obtained that there are going to be 3 dimensionless pi term. Next step is selecting the repeating variables. Okay. We will select D, rho F and G as repeating variables. Okay. So, first pi term can be written as, so what terms are remaining? V is remaining, right? Rho S is remaining and mu is remaining. So, the first term is going to be V into D to the power A, rho F to the power B and G to the power C. Okay. So, this is the first pi term. Now, we have to find A, B and C by in powers of MLT each to 0. Okay. And this will do in the next page. Okay. So, what we write is m to the power 0, L to the power 0 and T to the power 0 is equal to LT minus 1. This is because of velocity. L to the power A, this is because of D, ML minus 3 to the power B because of rho F, and G is LT minus 2 to the power C. Okay. All right. So, if we solve this, we see there is only one term for m. So, equating m, we will get B is equal to 0. Secondly, we will get 1 plus A minus 3B plus C is equal to 0. And thirdly, minus 1 minus 2C is equal to 0. This all together is going to give me B is equal to 0, C is equal to minus half, right, and A is equal to minus half. Okay. So, the first pi term that we are going to get is v is to the power, v will be v, correct, b is 0. So, what we get is v under root g d. So, this is the first pi term. The second pi 2 will be the second non-repeating variable, which was rho s, right, and similarly d to repeating variable will remain the same, d, rho f and g, d to the power a, rho f to the power b and g to the power c. All right. So, if we solve, you should do this. After solving, we can simply get pi 2 is equal to rho s by rho f. All right. You can solve this using the same procedure given here. Okay. Now, the third term, pi 3 will be the last repeating variable, which was mu d to the power a, rho f to the power b and g to the power c. All right. So, m to the power 0, l to the power 0, t to the power 0 is equal to m l minus 1, t minus 1, okay, l to the power a, m l minus 3 to the power b. Actually, I am just writing it down, to the power c. Okay. So, this will give us 1 plus b is equal to 0 minus 1 plus a minus 3b plus c is equal to 0 minus 1 minus 2c is equal to 0, and this will, after solving, it will give b as minus 1, c as minus half and a as minus 3 by 2. So, the pi 3 is going to be mu divided by d to the power 3 by 2 rho f g to the power half. So, we have got pi 1, pi 2 and pi 3. So, finally, the functional relationship will be pi 1 v by under root g d is a function of pi 2 comma pi 3. So, rho s by rho f comma mu divided by d to the power 3 by 2 rho f g to the power half. So, this is one of the this is one of the examples where we have solved this. Okay. So, another problem that we can actually go and do this. So, yes. So, another question which we are going to solve in Buckingham pi theorem is question number 6. So, it says that the efficiency eta of a fan depends on the viscosity of the fluid, the angular velocity omega, diameter d of the rotor and the discharge q. Expressed eta in terms of dimensionless parameters using Buckingham pi theorem as eta is a function of omega d square nu by q by omega d cube. Okay. So, here also we are going to use Buckingham pi theorem. All right. So, as always we will go on a white screen. So, you see the first step is solution 6 as in the question number 6 that we have here. So, this eta, this is the efficiency of the fan, is a function of what all variables have been told: viscosity nu, okay, omega, the angular velocity omega, diameter d of the rotor, and discharge q. All right. So, this is the first relationship that we obtain. The second, what we do is we write the dimensions. So, dimension is m to the power 0, L to the power 0, T to the power 0. All right. The nu is L square T minus 1, omega is angular velocity. So, it is going to be T minus 1, the diameter is of course L, and q is L cube T minus 1. All right. So, these are the basic dimensions that we have written. All right. And here how many dimensions are there? K is 1, 2, 3, 4, 5. And how many basic dimensions have been used here? So, you see in nu, omega, d and q, the dimensions that have been used is L and T. There is no mass, it is m to the power 0 in efficiency, right. So, it is only L and T that we have been used. So, R is going to be 2. All right. So, number of pi terms, this is an example also for showing that R is not always 3. 5 minus 2 is 3 pi terms. Okay. So, another next step always is we have to choose the repeating variable. So, the number of repeating variable should be same as R. So, select, we are selecting omega and d as repeating variables. Okay. All right. All right. So, first pi term is very obvious, correct. If we follow our regular procedure, what is the regular procedure? We multiply the first non-repeating with omega to the power a, d to the power b. All right. And if we solve this, we get a is equal to 0 and b is equal to 0, implies the first pi term is going to be eta itself. All right. Very simple to see that. Now, the second pi term will be the leftover. So, we can choose the non-repeating variable. One we have already chosen eta as non-repeating variable. The second will be nu. All right. Nu omega to the power a and d to the power b, or in other terms we can write m to the power 0, L to the power 0, t to the power 0 is equal to L square t minus 1 into t to the power minus 1 whole power a, and d is L to the power b. Okay. And after equating powers, m, L and t, what we get is 2 plus b is equal to 0, implies b is equal to minus 2, and minus 1 minus a is equal to 0 implies a is equal to minus 1. So our second pi term is going to be nu by omega d square. All right. So that is the second pi term. Okay. So now we are going to have the third pi term. So so pi 3 can be written as, so the last one is L3 t minus 1, so that is q omega to the power a and d to the power b, or we can write m0 L0 t0 is equal to L3 t minus 1 into t minus 1 to the power a and L to the power b, and by equating powers of m, L and t, we get 3 plus b is equal to 0 implies b is equal to minus 3, minus 1 minus a is equal to 0 implies a is equal to minus 1. Therefore, the third pi term is going out to be q by omega d cube. All right. So, the final expression is going out to be eta as function of omega d square by nu, or I mean it's 1 by pi 2 and q by omega d cube. Hence, so I will go back and solve the last problem for this one, Buckingham pi theorem. So there is a question number 10. This has so the question says an open cylindrical paint can have, so an open cylindrical paint can, okay, sorry, this is one paint can having a diameter d is filled to a depth h with a paint having specific weight gamma. The vertical deflection of the center of the bottom is a function of d, h, d, gamma and E, where d is the thickness of the bottom and E is the modulus of elasticity of the bottom material. Determine the functional relationship between the vertical deflection and the independent variables using dimensional analysis. So, this is a classical example of, we can actually go a little fast here, because in the two questions we have clearly laid down the procedure. So, but you see even in such complex cases where lot of terms, new terms are there, we can use Buckingham pi theorem for this again. Okay. So, how we do this is we go to the solution 10. Okay. So, we have seen that according to the solution, so vertical deflection delta is a function of d comma h, comma small d, gamma and e. Okay, and we can simply write the dimension. Dimension here is length L, d is also length, h is also length L. Okay, small d is also length L, gamma is FL minus 3, or we can write ML minus 2 T minus 2, E is FL FL minus 2 or ML minus 1 T minus 2. All right. So we have to determine the number of required pi terms here, right? So for now we will use FL and T. So this term, so we are going to use FL and T as our system, not MLT. As system. Okay. So how many variables? K 6, or reference dimension R is how much? You see, in FLT system it has only F and L, right? So that means 2. So number of pi terms is equal to 4. Okay, since there are only 2 reference dimensions, repeating variables, let us choose D and gamma. Okay, one representing L and one representing both F and L. Okay, so the first pi term D to the power A, gamma to the power B, or if we write in terms of L into L to the power A, F FL minus 3 to the power B is equal to F to the power 0, L to the power 0. Okay. So this will give 1 plus A minus 3B is equal to 0 and B is equal to 0, resulting in A is equal to minus 1 and B is equal to 0, thus implying that pi 1 is equal to lambda by D. Okay. If we follow same procedure, we are going to get pi 2 as H D to the power A, gamma to the power B thing, and we get pi 2 as H by D. All right, and pi 3 will be given as small d by capital D, and pi 4 is going to be E by D gamma. All right, and therefore we can simply write lambda by D is a function of H by D comma D by D comma E by D gamma. So, you can see how we have used the Buckingham pi theorem to solve our problems for dimensional analysis. And with this I will conclude lecture for now, and I will see you in the next lecture. Thank you so much.